Because I three of those
Hey.
papers were mine.
Seniors are taking their semester test. We gotta be quiet. All right. Hey. Good. Okay. All right. Today we're gonna take a few notes today. After that, we'll be done early today. I will hand out your practice semester test tomorrow because we're gonna start reviewing it tomorrow. Now, as I warned you earlier this week, as I warned you yesterday, I have book checks coming up. I'm going to move the due date for the book check-in. Hey. Okay. I'm going to move the book check-in date to Monday next week. Why? Okay. Hey, can we stop talking, please? So, book check-in date is Monday now. The reason being I'm not going to be here Friday, so you'll have a sub. Even though I know we're supposed to review the semester test, I'll already have the class pre-recorded. I'll record my class doing the normal thing where we go through the first half. Second half of the days we always reserve for the semester review. We'll start that tomorrow. You'll see how that works. So we'll do a little bit of notes in the morning, then we'll switch to the practice semester test. I'll give you those out tomorrow. But Friday, I'll have it pre-recorded. So if the sub doesn't have the technology quite working right, they just don't know how to get started, it's not working right, I recommend that you bring headphones to class.
Headphones?
Because I'll already have it posted to the website, so you can just watch it on your own.
On both Thursday and Friday?
Why can't we just play it
Friday.
on there?
Why can't we
So
just play it
Friday.
in groups
So,
per se?
No.
Per se.
No. So
Friday?
so for Friday, just make sure that you're ready to go. The notes will be up there. You can kind of watch me go through it. I'll try to explain it. Maths test, if you haven't finished it yet, make sure you're taking that. My test retakes have to be done by Friday this week because I'm not here. They have to be done pretty much by Thursday afternoon. So if you're going to retake it, that means you have to come in the morning. I already had one person come in this morning to retake. So if you're going to do that, you have to come in. Okay? The people that need to finish my semester tests. Nope, everyone in here is done. So good. Okay? All right. Questions, comments about the little stuff coming up? Okay, you need to take out your notes today.
How many days of notes? Or how many pages will we need?
It's been like over a week already. Like a week.
Like, do you think like for this section, like 4 pages would be enough? Would you rather have candy?
Yeah.
Like 2 front and back?
What kind of business are you running here?
Alright.
Awesome one.
Do you have conversion rates for how much a candy is worth based on a penny's value or what?
Alright.
Half a penny is worth.
Hey, I can't handle this today. Okay, we gotta stay quiet today. Seniors need to finish up their semester test, and you guys need to pay attention to this.
Tori is disturbing me, actually. I can't. Everybody's coming in. Can I sit in front of Dane?
Okay, hey, are we good to go?
Yes, sir.
Okay, alright, notes today. We're moving on to sections 6, 7 today. We have a couple things we're gonna mix. So I'd like you to write this stuff down today. The goal is to talk about vectors, but also go on to more important topics. So, goals today. I want to do a quick recap of what a vector is. We'll talk about how to find magnitude. Okay, let's stop talking, please. Otherwise, I'm going to start moving people. So, magnitude. We'll talk about how to find direction. And then the last thing is today, and this is the new part for this vector part, we're going to find angles in between objects. We're going to find angles in between. Okay, and angles to what I call in between the x-axis and where the vector sits. So this part is new, we haven't seen this yet. We'll talk about it. It's common sense, you'll need a calculator for it. But the goal is to get to the new stuff today, which is 6, 7, which this stuff is called dot product.
Didn't we already do chapter 6?
We did the first couple sections of it, which was based on law of sine, law of cosine. But this stuff was like radically different. So
Why did they put in this chapter?
I'll explain. It's going to come up with like these last couple rounds. We'll see it. All right. So dot product. We're going to go through the formula, what it is. I'll try to explain the best of my ability of like why we have it, the importance of it. That's what we're going to look at today. And then to get to your question, this is what I was going to get to today, was to do a time, why do they have it in chapter 6? Like, why are we doing it now? What are we going to do with it? Okay, that's what we're going to talk about, and that comes in with the importance of it. Okay, so this is kind of our goal. It's pretty straightforward stuff, but once we get to this later stuff, it can get challenging, so I'll try to explain it to what I want you to be able to do, okay? Let's talk about vectors first, okay? A vector, just a reminder what it looks like. A vector it looks kind of like a ray, but for us it's actually a line segment, even though it has an arrow, because it has direction and it has a size to it, like a magnitude, a distance. So here's the idea. This is what a vector looks like. Let's call it vector W, and I'll say this is 2i plus 7j. Like, I think that was an example we used yesterday. It has an I and a j component. That's basically the x and y component when you draw it. So you can put vectors anywhere, as long as you're going the same direction. And how you find direction is that you use slope, basically. Slope is taking the y number over the x number. So this thing is going to have a slope, of 7 over 2, right? It's the y component over the x component, j over I. And so what 7 over 2 is, that means it's a positive number, it's going up to the right. So if your vectors have the same slope, they're going the same direction, they're either parallel or they're coinciding, they're collinear. Okay, however you want to say it. Because slope gives you a direction where it's going. Well, how you can do this, you don't need to find slope, right? You can actually just draw this anywhere you want, as long as you use the numbers, 1, 2, 3, 4, 5, 6, 7. If you just use the numbers, 2 over, 7 up, you can actually draw the vectors where you need to put them. I always start on the origin, and then I just go from there using the I and j component, and this is vector W. So you can see it's going up to the right. My slope told me that, right? It was 7 over 2. Perfect. Okay.
Slope is j over I.
Alright, is there any questions with what a vector is?
Slope is j over I.
Yeah, slope is j over I. It's the y component over the x component. The book, I think they call them the a and b component. It's I and j, that's just what I use. But that's how you find slope. It gives you kind of a direction where it's going. The problem is, it doesn't tell you the size, it just tells you the direction you're going. To figure out size, there's 2 ways to do it. You can either use Pythagoras Theorem, or you can use what they call the magnitude formula, which is the Pythagoras Theorem just with fancy words. So, Pythagoras Theorem is, if you had a mock drawing, this is the number 2, this is the number 7, and it is a right triangle. You can find the distance or the magnitude of that length, right? Because how you do it? So to find distance or magnitude, this is what it says for magnitude. It's the name of the vector with 2 bars. It looks like actually value bars on the other side of it. So this is going to be 2 squared plus 7 squared, and then you're going to take the square root of it. Because that's how you do Pythagoras Theorem, right? You take a and b squared, add together equals c squared, which is the distance we're trying to find, that's the magnitude. And you just take the square root of those 2 numbers. So whatever this number is, that's 49 plus 4. That number, was that 53? That number is the magnitude. That's how long that particular vector is. Now, for vectors to be actually equal or congruent to each other, they have to have the same direction, basically the same slope, and they have to have the same magnitude. So that's something like, the book will try to compare different vectors to each other, but they have to have the same magnitude, same slope, everything has to be the same.
direction?
Yeah, that's slope. Slope tells you that.
It was positive going up.
Yeah. All right, questions on what magnitude is, the basic stuff about vectors. Now, what we talked about yesterday was how to find, how to do basic vector addition, how to do subtraction, all that good stuff. We talked about if you want to make a vector in opposite direction, you put a negative sign in front of it. So what that does to your vector, it makes both numbers negative. It makes both numbers negative. Now if they're already negative, it turns them positive. So this is what the vector will look like. So that vector is going negative 2, down 7, 4, 5, 6, 7. And so this is the vector. It's going the complete opposite direction of what W was doing earlier. That's negative W. Makes sense? You just distribute the negative sign through. Now, why this is important is because we can add vectors together. Vector addition is really straightforward. Now, whatever 2 vectors you have, let's call it V, let's call it W, let's call it vector Z. Okay, we have 3 different ones. I can give any numbers I want, so let's call this, let's use the vector V is 3i minus 6j. Let's go with W is the 2i plus 7j, and z is going to be negative 4j. That's just what they list, so there's no I component. Right? So it's a 0I.
And this is for like motions.
Yeah, so we'll talk about like how to put it together and talk about directional bearing and all that. So, all right. So how this works? What the book will ask you for. What the book will ask you for, it'll do something like this. Okay, this is what the book will ask you for, that's vector addition. They can put it with a big, long, complicated math problem, but what they want you to do is subtract the two vectors from each other, then double it, that's scalar multiplying it, and then add it. Well, if you have to draw this picture, like you have to draw a sense of scale, what this is doing is you have to figure out where v is going. V is going 3 over, 6 down, 1, 2, 3, 4, 5, 6. All right, so here's vector, vector v. And we're going to attach w minus z, but we're going to double it. So I have to figure out what w minus z is. W minus z is basically, w is going over 2 up 7. So if I draw a mock picture of that, that's over 2 up 7. Okay. And then negative z is going negative 4j. So that's positive 4j. So you're going to be adding a 4j onto w basically. So if you want to like figure out what that vector looks like, what v or w minus z is, w is going over 2 up 7. Z normally goes negative 4j. So negative 4j is going down negative 4. But since we have a negative, we're subtracting it. This is going to be going positive. Now why this is important is because that vector, when you actually subtract these, this line right here going from the starting point to the end, that vector is w minus z. So if you do the numbers, you can see what that vector is, right? That it's 2i plus 7j, and you're adding a 4j on, because we had a negative.
So just 11j.
So it's 11j. So that makes sense when you actually look at the picture, that it's 2 over 11 up. And that's what made sense. Well, that's what it's doing here. I'm actually going to be adding 2 times whatever that is. So if, this is 2 over 11 up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? I'm doing that, and then I'm going to double it again. So this whole vector is this, right? That's 2 the w minus z's. Well, the idea is that my final answer for when you add these two vectors together, again, this is the w minus z, and I'm doubling it. This is my final answer. Like, this vector is what they're looking for, that final answer. So I can tell you, like, it's going to be probably in the positive.
It's a big picture.
Yeah, it's big because we're
Pretty
stretching
huge,
out further,
actually.
but how we're actually doing this, this is w minus z, we're going to double it, and we're going to add that to v, because this is what they wanted me to do, right? They wanted me to do this. Well, we already figured out w minus z was 11, or it's 2i plus 11j. We're going to double that, and we're going to add that to v, and v was 3i plus, minus 6j. So the idea here is this is 4i plus 22j's. We're going to add that to the 3i minus 6j. And you're going to add like terms together. So it ends up being 7i's. This is 7i. And if I add those together, what is 22 minus 6? What is that? 16? That's 16j's. That's my final answer. Like, that's the vector that I'm coming up with. Okay, do you see how vector addition works?
Yeah.
Now, why this is important is because the concepts of what we did earlier is that there's actual angles for these vectors. Vectors are tilted at very specific angles, and we can actually mix the stuff we did in chapter 4 and 5 with this stuff, and actually do these as a form of law of sine, law of cosine problems, which is the important stuff. And I'll try to give you an example of that here in a little bit, like what you can do with this stuff, so you can actually see the numbers that are involved, and how you can actually come up with numbers. But does everyone understand how we can do vector addition now? You can like add pieces again. I'm just adding the i's and j's components together. If I'm subtracting, fine, you just do the normal subtraction rules. But the final vector, this is the part that people can't figure out, is like, what does this actually mean? It means this. It's the line where you started to where you ended. That's the vector that you're coming up with when you do all of this math. It's the actual length of it, and that vector has a specific length. So, and this process, you could actually save some time on those law of sine, law of cosine problems if you knew how to do this stuff. Because you could put these problems as vectors and make them with an I and J component, and then you can figure out the length of them really quick without having to deal with a lot of extra stuff. So, all right. So, let's go to how we can find angles. How you can find angles between objects.
Mr. Ward,
Yeah.
what's 64 minus 48?
I don't know.
Come on, you can at least make an effort.
Beat me.
I can't do that one.
I don't know. Okay. Sorry. All right.
You were only 2 off.
I can ballpark it. I just can't figure it out. It's weird.
One time you said it was 36.
Yeah. It switches. Catch me tomorrow. I'll probably say it's 40. So,
It's 40.
all right. So, hey.
64 minus 48
All right.
less than 8.
Magnitude and direction. So angles between objects. So let's say that my vector is right here. And this vector, let's say it's, let's call this vector M. And the vector M itself has an I and J component of 5i plus 4j. Let's say that that's what it is. And I wanted to figure out the angle that it makes with the x-axis. That angle right there. Well, here's the trick. It's basically just a triangle, if you can see it, where this is the 5, that's the I component. This is the J component, that's the Y numbers going up. You can actually figure out angles because you can use the trig functions. You can, if you do the Pythagoras Theorem, where you find magnitude basically, if you do the magnitude of m, that'll be the length of the hypotenuse, the actual vector itself. So that's the square root of 5 squared plus 4 squared. So that's 16 plus 25, which that's 41.
How did you know that?
I don't know. All right. So,
That was good.
all right, but the square root of 41. Now that I have that, now I can figure out the angles that this thing is made. So like for instance, I can do it by any form. I can do it by tangents. I can do it by cosines and sines. But how this actually works is that now that I have those, I can do this. That the cosine of theta is the adjacent wall over the hypotenuse wall. And then you could take the inverse cosine. You could take the opposites. I could do sine.
That's easier.
No, I can do sine. So sine is 4 over root 41, right? Sine of theta. You could do tangent.
And you don't have to mess with them.
Yeah, you could do tangent. And you could go the 4 over 5 route. Okay? And then you take the inverse tangent of the other side. But there's different ways of finding the angles that it makes of the x-axis. And why that's important is because this can help you find missing pieces. So if you know how long a vector is, and you had an angle that it makes with the x-axis, now you can actually figure out the lengths of the vector itself. So the actual I and J component, depending on what it is. Like, because one of the problems in the book that I saw was that an airplane is flying 20 degrees, it's flying 20 degrees northwest. It's flying 20 degrees northwest, and the actual like distance it flew was 186 feet. Feet. Okay, it didn't go very far. It just came out the runway. And it wanted to know the vector. It wanted to know the vector that it was taking for the I and J component. Well, that's fine. This is basically what we're doing. That here's the angle. It's going 20 degrees northwest. This is 20 degrees northwest. So that means this angle here is 110 because it's 90 plus the 20. So that's 110 degrees. And the idea is that you can use that 110 to figure out the I and J component. Because the 110 can transfer over. You can use this smaller angle on the inside, which this would be 70 degrees, right? And you can figure out the I and J components for it. Does that make sense, like what we can use this stuff for?
Yeah.
And then you can figure out the actual vector that aircraft was taking.
I don't like, is that gonna be on the test? Cause last time you said it wasn't
No,
gonna be, and
this,
then it was.
this stuff, the stuff I would expect you to do is vector addition. Be able to add vectors, subtract vectors, draw a mock picture where they're going. Dot product.
And the triangle.
Yeah, but I mean, that's magnitude. You'll have to be able to do magnitude.
That is fun, we can do that.
Okay, alright, hey, are we good to go on to the next part? Dot product, that's the new stuff. That was just something like we've done previously, that you were mixing like old stuff with new stuff so you can figure out vectors.
Now we're doing the dot product?
Doing dot product, this is brand new today. Brand new.
Brand new dot product.
I'm scared.
Okay.
Sorry, but it might eat me. Is dot product gonna eat me?
Nah.
I'm gonna eat you alive, Lars.
Okay,
Hey, Mr. Ward, I have a question. Have you had Brody Banky for geometry yet?
not today.
You will be. What about Isaac Knudsen?
I haven't played
So you're not gonna tell me to eat the paper? Are you not gonna tell me to eat the paper?
Okay,
I bet
hey,
you have students
let's go through
that
dot product. Alright, first of all, we've done scalar multiplication. Okay, scalar multiplication is pretty easy with vectors, vector multiplication, right? It's where you're taking, I think we did a problem earlier where we took 2 times w, right? Where if the vector w was the 2I plus 7j, you can multiply it by 2, and each of the numbers you can take times 2. Okay, so we multiply both by 2, and so 2w is actually 4I plus 14j. That makes sense to a lot of people, like that's scalar multiplying. That isn't dot product. Dot product is something completely different. Here's what it looks like. Okay, this is dot product. It looks like you're just taking 2 vectors and you're going to multiply them together.
But it's not.
But it's not. Because the only type of multiplication we've had up to this point, because I guarantee this stuff is on your test, so you want to figure this stuff out. Okay, so dot product. We're not just multiplying the 2 vectors together. You're actually taking the I components and j components and kind of figuring out a number that's associated with it. Okay. Now, if you want to, like, so a lot of you like to know the pages. Again, this is section 6-7. What page is that? That's page. What page is this? It's page 713. Okay. All right. So here's how it works. If you have your vector v and you have your vector w, I'm going to use the same w I've been using before. Vector v. I don't know. Did I have the vector v earlier?
Yes.
Yeah.
What was the numbers?
I have no idea.
Let me check my notes.
Was it like 7 plus 4? No, 2 plus
Oh wait, I got it, I have it, just wait.
Say again?
2I plus 7j.
Yeah, I already have it.
Never
That
mind.
was W, not
It might have been 2.
B.
I want the one. I had it today.
Oh, that one.
It was that one? Okay, perfect. All right. Now, for dot product, here's how it works. You take the I components and you multiply those 2 numbers together. Okay? We're going to multiply that. So we're going to take 3 times 2.
No. That went harder.
And then you're going to multiply the j components together. So that's -6 times the 7. Right? You're multiplying those 2 numbers together. And whatever you get, you're going to add this together. You're going to add those 2 results together. And the dot product actually turns out to be a single number. Yeah. It turns out to be a single number. And so the idea is this turns out to be 6 minus 42. And then you subtract that off and you get a -36.
How are you doing so good today?
I don't know.
Have you already done this problem? You've done this problem.
He's memorized these.
I had to memorize the addition subtraction. Alright, now.
Wait, why?
I knew that you got that 41 way too
Way
quick.
too quick. Alright, now.
You
Now,
add them, you don't subtract them,
multiplied the
stop
2.
product.
I did. I took 6 minus 42.
Because -6 times 7 is a -42.
Alright, now, what this is, what dot product is, if dot product turns out to be 0, dot product turns out to be 0, then the 2 vectors are at 90 degrees from each other.
Perpendicular.
Perpendicular. If the dot products turn out to be 1 or -1, they're in a straight line, they're parallel or they're coinciding, they're collinear with each other. We use this little math to figure out when there's 2 different vectors on a page. what's the relationship of them if you were to attach them to each other?
Hugs. How
So-
do you just attach them?
Because you can move vectors anywhere you want, right? Because vectors just have a direction and a magnitude. So like it doesn't matter that I always have my vector starting at the origin, right? And going like over 2, up 7, right? Whatever that is. I can move it anywhere I want as long as it's going over 2, up 7.
But why would you want to connect them?
Maybe we're doing addition. So like one of the book prompts that they always say is like an airplane's taking out, is taking off from an airport. It's going, at a certain direction, 120 degrees, whatever it is. They always use angles. But it's going at a certain angle, and the idea is that it's got a crosswind of 40 degrees. Well, if the crosswind means going across the plane, it's not going ahead or tail, it's going cross. Well, the idea is that it's shifting, so if the wind's going this way, it's shifting the plane to a different path, and it doesn't even know it. Like, you'd be thinking you're going in a certain way, but the wind is actually carrying you slowly by slowly. It's like when you jump in the river and you try to swim across. It carries you downstream a little bit. Maybe not very far, depending on how it's... Yeah, and that's the thing. Like, if we had still wind, we wouldn't have to worry about it, right? You'd go the direction you're intended. But if the wind is there, we have to compensate for it. So, and that's what's happening here. This type of math is to set to figure out what type of angle you have.
What do we do with the I and the J?
So what's the negative 36?
Those symbols go away for right now. We're looking for just that number.
Drop them?
Now, how this works.
Connect? And we
So-
connect them?
Yes.
Connect
So,
them?
6 to the negative.
how this works, what dot product is. You guys saw the math there.
Yes.
Connect
Okay.
what?
This
Wait,
is the
so it's like
formula
connect
for
the
dot
dots.
product.
Connect 4. Drop them and connect.
Okay.
There's no proof.
This is your second formula for dot product.
Looks like voltaic
Okay,
formula.
so how this works. The dot product is on the one side, so we just found the negative 36. Okay, we just found that. What we're going to have to do now is find the two magnitudes of my two vectors. So the magnitude of the first vector, that's the 3 squared plus 6 squared. So this one is 9 plus 36, and that turns out to be 45.
Yeah.
And this one over here, we just figured this one out a little bit ago. That was the 4 plus 49, so that's the 53. We're going to multiply those two together.
Where is he getting
And-
36?
Negative 36 is from right there.
No, the 9 and the 36. Where did you
That's
get-
V, it's squaring both the I and J component. And then when you square them, they turn positive. You can add them together, so 3 squared plus 6 squared. And then the cosine and angle between. Now, why this is the case? If you have a negative number in there, okay, if you have a negative number for the dot product. Now, before I said if it's 0, you have 90 degrees. If you have 1 or negative 1, that's 180. But if you have a negative number for the dot product, your cosine is an obtuse angle. So when you actually attach the two vectors, like to each other, like this on a coordinate plane, 2, 7, 1, 2, 3, 4, 5, 6, 7. Here's the first vector, that's vector V. That's W, sorry, that's W. And we attach that to the other one, which is 3, negative 6. 1, 2, 3, 4, 5, 6. So there's that vector, this is vector V. The angle in between them is obtuse. And how I know that is because when I actually solve this, it'll actually tell me the angle in between the two vectors. So this is what you're actually seeing here is a version of the law of cosine. And that's what I wanted you to see, okay? All right, so to do the math here, we actually have to multiply these two numbers together. Geez, what is that?
A lot.
3, 15, 31, 13, 0, 25, 32, 22. That's square root of 5, 8, 3, 2. Cosine 8 of 36. All right. Again, that number is 2385. All right. And again, what we're going to do there, you'd actually take the square root of that number, whatever that is. It's a weird number. You're going to divide it over, and then we'll take the inverse cosine.
So we can use the decimal approximation in this?
Yeah, on this one, we're just going to approximate it. So, negative 36, we're going to divide by the square root of 2385. And that's going to equal the angle that's in between them. And that's why we use dot products, to figure out angles in between two vectors. Especially when there's like crosswind and whatnot.
And it works every time.
Works every time.
That's incredible.
Yeah. I'm going to type this in just so you can see this. typing this in, what do we have? We have negative 36, we're going to divide by the square root of 2385. This turns out to be a negative 0.7372, and we're going to take the inverse cosine of it. So the inverse cosine of negative 0.7372, we get 137 degrees. And again, how I just figured this out, I took the inverse cosine to the other side. Where'd my calculator? Okay.
What's supposed to get?
Hey, are we good with the 137, how we found it? Again, dot product has two steps. To find dot product, you just multiply the i's and j's, you figure out the number. This number tells me what type of angle it is roughly. And then you use the second formula to actually figure out the numbers between them. So this is what we'd use on those problems when you had two different things going on, ground versus a plane. Or you had boats going two different directions and you're trying to find the angle in between the two boats. That type of thing. And then we can use this stuff to actually find the distance between the two boats later.
I thought there were planes last time.
Planes, boats, whatever you got.
How about trains and automobiles?
Sure.
What about bears? Can we find the distance between two bears?
Probably just have
What
to.
if the bears eat?
That's it for today. That's all I have.
Can we find the distance between